behalf of the IEEE Computational Intelligence Society, I would like to welcome our webinar speaker, Professor Simon Lucas, who is going to talk to us on simulation-based AI with large language models. Simon is a full professor of AI in the School of Electronic Engineering and Computer Science at Queen Mary's, University of London, where he leads the Game AI Research Group. He's had many numerous roles, and he has recently spent 2 years as a research scientist, software engineer in the simulation-based testing team at Meta, applying simulation-based AI to automated testing. Simon was also the founder, editor-in-chief of IEEE Transactions on Games and co-founded the IEEE Conference on Games, was vice president for education for the IEEE Computational Society, and has served in many conference chair roles. His research is focused on simulation-based AI, bandit-based optimization, and large language models. Without further ado, I will hand over to Simon for this really exciting webinar, and thank you so much.
Fantastic. Welcome, everyone. Thanks, Keely, for the introduction and indeed for inviting me to give this. It's a real pleasure to be talking about what I think is an absolutely fascinating area of research. So here's an outline of the talk. And I think one of the main points is that despite amazing progress in generative AI, we all use it all the time. I'd say even the best models have serious and arguably insurmountable limitations in their reasoning abilities. On the other hand, simulation-based AI makes intelligent decisions based on devising and simulating a range of possible plans. And the idea is we do a lot of simulations and we choose the course of action that's most likely to lead to a good outcome. So it's a really kind of simple and compelling idea. So in this talk, I'll outline what I mean by simulation-based AI and show how that can ideally complement LLMs. And I'll give some examples, including a maritime capture the flag competition that we used very successfully in this, and talk about some examples and the future of this area. So what I really think is that SBAI and LLMs, they're really a fantastic combination to get the next generation of agents. And I see 4 distinct paths to this. So one of them is you can use LLMs. LLMs are really great at writing code, and in many respects they're superhuman at writing code, and in many respects also, they're not as good as really good human programmers. They've got very clear limitations, but for a lot of code, they're very, very good at generating code. And so a natural thing is to, if we consider heuristic search algorithms, can we use LLMs to enhance these algorithms by generating better heuristic functions? And this already works, right? This is kind of low-hanging fruit, and people have been doing this for several years, I would say, with great success. At the end of the slide, I've got some references to more work on this. So this has been used a lot already in combinatorial optimization, and I would say it's been used less so in SBAI, but we've already been doing a bit of this with a moderate degree of success, and I'll say a bit about that later. So another approach is algorithm development, and again, this has been done a bit already, but I think there's really a lot of scope to use LLMs to, in a directed way, generate new algorithms. So I'll come on to some classic SBAI algorithms soon, but for example, a very common one is Monte Carlo tree search. And then a variant of that is Monte Carlo graph search. Now, in going from the tree representation to the graph representation, it turns out there's quite a lot of detail to get right to really make it work well. And this is a type of search that I think if we point LLMs in the right kind of direction and use very good ways to evaluate how successful each variant is, then we should be able to come up with really powerful new algorithms in a very kind of directed way. And this also applies to things like hierarchical planning within the area, using density estimates of various areas of the search space. And so if you're trying to explore more, you want to go to sparser areas. So we have concepts like sparsity search. And we can use LLMs all the time to help generate these new algorithms. And then the third one, I think, is very much underexplored. And the idea here is that you use agents to make best use of the available simulators that you have. So you might have a whole sort of suite of simulation software for a problem. And if you give it to an expert engineer, they'll spin up simulations that are very appropriate for the particular decision at hand. And at the moment, we don't do this much at all, I would say, in AI. So the idea here is to get LLMs to optimize the use of simulation software, simulation APIs in very kind of directed ways. This could be as simple as just controlling the size of delta t in a physics simulation, but it could be way more involved in that. And it could include doing things like choosing opponent models. And then the final one, and this is, I think, really fascinating, is to use LLMs to assist in the construction and refinement of explicit world models. And in this particular way, I mean through code-based simulations. So you find, repurpose, and generate structured simulation software. Now, within the whole kind of area of learning world models, lots of people are doing this using deep learning with varying degrees of success, and in some cases very impressive results. Many of you will have seen the Genie system from Google DeepMind that learns models of 3D video games. But one thing to emphasize on the deep learning methods is that they tend to be trained on massive amounts of data and from pre-existing simulation software. So in that case, the video game is acting as a simulator to train these really sort of vast and complex models. And by focusing on code instead, we can get things that are, vastly more efficient and also amenable to understanding and adaptation to new problems. All the kind of things that we like about software in general. We can develop lots of tests for them to check that they do what we want them to. So I come very much from a games background, and we use games to evaluate the quality of these methods. And one thing I just want to give a mention to is the tabletop games framework. This was developed within our group. I've not been directly involved in it, but there's the website there, and please do look it up. So within TAG, we focused on really sort of complex board games. So things like, I think one of the most complex ones for any board game players there is Terraforming Mars. So these are really, really complicated games. And it turns out that LLMs are really terrible at playing even simple games. And I think this is really sort of interesting to know, because if you use things like ChatGPT and DeepSeek as much, and Gemini as much as I do, you'll often be blown away by the apparent detailed understanding of sophisticated problems that these LLMs have. And yet, if you give them the kind of tactical or strategic reasoning problems that arise naturally in games, that they really, really are terrible. And I think this is an interesting thing to explore further. Just a little bit on the value of search. So I call this whole area now simulation-based AI. It's also called search-based AI. I'd just like to stress the importance of the simulation part, because in many real-world problems, we don't actually have the simulation, so we have to develop it before we can apply search-based AI to the problem. And that's why I really put simulation at the forefront of this. But this is from a recent YouTube talk by Noam Brown, who's at OpenAI now. And he's talking about when he did his PhD at CMU on poker, he developed Libratus, champion, really kind of world champion standard poker player. And what he observed as he was doing this was that he was spending a long time training the models, weeks, days or weeks of computer time to train the models. And then when they came to making a decision, it was just, it'd be done in a few milliseconds. So he said, well, hang on a minute, why don't we use some of this speed at inference time to do search instead? And so he did this, and that led to a big success. And what he said is that 20 seconds of thinking time was worth 100,000 times bigger training time or model size. So that's just an emphasis of the value of search. So what is simulation-based AI? Here's what I mean by it. So it assumes that you've got a forward model of the problem, and you're going to use this to consider future possible scenarios. You're then going to make decisions based on the statistics of previous simulations. And very often you can start with a random action or policy. You work to more favorable outcomes, and we often use bandit-based algorithms to balance exploitation with exploration. And this works very well with learn, policy, and value functions, similar to AlphaZero. And on the left here, we've got two pictures. The top one is illustrating Monte Carlo tree search. This is a simple problem with a binary action space. So at each decision node, I can either go left or right. And it turns out the reward function has been set up in such a way that there's more likely to be more reward if you go right. And this is just showing the ability of the algorithm to do asymmetric search. And so because there's more reward to the right, that's the way it grows the tree more. And an interesting thing about the kind of vanilla version of MCTS, and I would say, these algorithms, there are literally hundreds of variants of them, but in the vanilla version, each one of these thin lines on the left is a rollout. And for each rollout we do, we just add a single node to the tree. And then we're going to make a decision based on which of the actions leads to the best node from the current decision point here. So here we're going to go right because that had 27 successes out of 43 versus 3 out of 7 on the left. So this is the most visited node, and we'll use that heuristic to make a decision to go right there. The picture here is meant to illustrate the difference between MCTS and rolling horizon evolution, which is one of our favorite algorithms in our group. And here what we're doing, we're using evolution in real time within the decision-making loop. And we've started with random rollouts, a bit like one of the random rollouts in the top picture. But what we're doing here is we're evolving the complete solution. And so this is quite good at long-term decision-making problems where we want to have a long-term plan that we're going to stick to, but keep refining all the time whenever something better comes along. And the key thing to realize is that all of this only works if we have a good enough simulation. So the simulation is often key to solving complex real-world problems. So let me just pause this for a minute. So I've spoken a bit about what SBAI is. So why would we use it? Well, it's very attractive because we get immediate intelligent behavior. So that means we can change the details of a problem, and provided we made those changes to the simulator, then the search-based algorithm just naturally start taking advantage of that. And we'll still seek to get good decisions based on the new model. So these are also anytime algorithms. So typically the more computation budget we have, we're going to make better decisions. But very often we can make good decisions with a small budget. And we just need to have a fast and copyable forward model in order to apply them. And the simplest algorithms, as we see in a minute, are just a few lines of code. And the other good thing about this is that the algorithms are somewhat explainable. And by that I mean we can run the simulations, see the likely outcomes, and understand why the algorithm is choosing a particular course of action. So some other features, we can immediately tune them. We can change the rollout horizon. So that's what we're picturing here. So on the top right, when I run the video, these pink lines over here, they're showing the rollout horizon of where the ship's expected to be based on different rollouts. And then the lines on this graph here are showing the expected reward on each of them. Yeah, so like I said, I think it's a bit incredible that sometimes these random rollouts already can lead to good play. And also interesting, whenever the rollouts, even if the actual estimates of value are quite poor, providing there's information in the rank order, that can be enough to make good decisions still. So let's just run the video now. And you'll see it crashes a lot with a short rollout. Well, we can very quickly tune it now. I'm just changing it to have longer rollouts. There's a more interesting graph on the left. And the ship's trajectory is now going further ahead. And it's going to choose both trajectories, and also it'll aim to fire the bullets that hit the planets. And it does that quite successfully. So let's have a look at the simplest version of an SBAI algorithm. So this is rolling horizon evolution, and this is the simplest version of RHEA. It's called a 1+1 evolutionary algorithm. So to solve planning problems in real time, we just keep running this all the time. So let's just say we're trying to play a game. Then at the very start of the game, we'll have this best sequence of length L. In the last version of asteroids, that L was 100 steps into the future. And Each time I've highlighted random in green or mutate in green, this is just indicating that in the simplest version of this, these are just uniform random choices, right? But it's very easy to actually plug in a policy function where instead of making uniform random selections, we're doing a very biased selection. So we use a softmax distribution over the set of possible actions, and we just sample from that. So we're applying the policy. So it's still somewhat randomized, but we control this with a policy function. In the previous example, it didn't have any policy function, it was just uniform random. So we start off with this random sequence of actions of length L, and then for every decision that we have to make in the game, that's every time step in a video game, we say the best sequence is a shift and random append of the best sequence so far. So we use a shift buffer to maintain the current plan. And then this other key parameter of the algorithm is n-eval. So how many mutations and evaluations are we going to make each time? So each time around the n-evals loop, we say that mutsec, the mutated sequence, is a mutation of best yet. And if the score of this is greater than or equal to the score of the best sequence so far, then we just say best sequence is equal to the mutated sequence. And then at the end of those n evaluations, we return the first action in that sequence. And we just keep on doing this. So it's a pretty nice and simple algorithm. We're now seeing the exact same algorithm. So I haven't changed a single thing. There's been no retraining, nothing. It's the same algorithm. Now playing Planet Wars. We'll come back to a version of Planet Wars later. So I think the RIA is playing against a hand-coded heuristic algorithm, and it's making decisions just based on the statistics of the outcomes, and it's at that point overcome the opponent. That's a representation there. It's just a sequence of actions coded as integers. Each time we mutate them by changing some of them. In the case here, that particular sequence led to an expected score of 93. We made some changes. The two there I've identified, maybe some other differences too, in case you're really sharp-eyed and can spot them. And that modification led to an expected score of 472. So that mutation gets accepted. So for more details, please see our IEEE Transactions on Games paper with the authors here. So I'm one of the co-authors on this, and plenty more details there. And then there's what I mentioned previously was a basic RIA algorithm, and I already said that you can modify it with a policy function. Well, interestingly, when you play multiplayer games, you even start at just 2 players, then you also have to consider the actions of the opponent. And I just want to give a shout out to some work I was involved with, led by people at the Institute of Automation at the Chinese Academy of Sciences, these authors here. And this has just been nominated for an IEEE Transactions on Games Outstanding Paper Award. And this was a competition winner for the fighting game competition that's been run as part of IEEE Conference on Games for many years now. So it's a highly competitive game. So it's 1v1 real-time combat, 10 millisecond response time, frame-based animation, vast space of combo moves, health and energy system, and multiple characters with different strengths, and the bot has to play as different characters. So what we did here was to train opponent models. So when you use RIA for these 2-player or multiplayer games, as you roll out your own plans, you also have to make assumptions about what the opponent's going to do. And here we used trained neural network models to have better opponent models, and this was highly effective. And that's just one example of how we can take the basic algorithm and very significantly improve it. And this also feeds into the idea that actually we could use LLMs to help with this. So we can use LLMs to come up with opponent models as well. And then another variation on this, this is work that's as yet unpublished, but we can also apply multi-unit RIA for multi-unit control. And as soon as you have many units to control, in this case it's a kind of foraging problem where we're controlling 10 units, then you have a combinatorial action space. So the many, it's a huge branching factor in the problem. And we have to probably innovate a little bit to make it work well. And one thing that you can do is to evolve plans for individual units selectively. while caching the trajectories of others. And that's the main idea behind Muria. And we see in this example, we get significantly better performance in that way. The main point being here is that although the kind of core is simple, there are many, many ways that we can develop these algorithms to get better performance on a range of problems. Okay, so that's a bit about simulation-based AI. We're going to look a bit more at some of the capabilities of LLMs. And, you know, we use LLMs so much all the time. I want to focus a little bit now on some of the things that they can't do. So can LLMs play games? I think the first approximation, and actually, you know, you might see some contradicting reports showing that in some cases they can, and it does depend on the game. It's a bit more nuanced than I might be presenting it. But there's a really nice recent paper called GT Bench. It's the one illustrated on the right here, and they found some very interesting things. So they had a range of, I would say, fairly sort of simple deterministic games. And what they found is that the LLMs playing as agents, and they had various versions of LLMs, including various kind of scaffolding, such as chain of thought, tree of thought, various others. And actually, the LLMs, including their scaffolding versions, lost nearly 100% of deterministic games. That's games like Connect 4, Breakthrough, and Tic-Tac-Toe to MCTS. And now MCTS for some of these games is playing like really strongly. And they found that the LLMs are slightly better in perfect information games, but still not as good as more sophisticated methods. So the kind of first approximation takeaway would be that LLMs, you know, that they can't play games, or at least not to a good standard against good opponents. I think I don't have time to dwell on this. I just want to give a shout out to this paper as well. That's also comparing LLMs now against human game players, and finding on this range of games that the humans, which are over here, are significantly stronger than all of the LLMs under test. So one of the things, you know, all the time we're looking for ways to benchmark LLMs, and their ability to play games is still one good area for doing this. So there were games for which we might not expect LLMs to be particularly good. LLMs excel in language. So the current demo now, the Griddle AI demo, is for a language-based game. This is a game that I developed, and here's the idea of the game. So you've got a grid of letters. So you've got a grid that starts empty. It's going to be easier actually if I just run the game and talk you through it. So let's behind the scenes, there's a deck of cards, and if you put in a random seed, I put in random seed 2 because I know it needs a reasonable bunch of letters. In fact, they all do, but this is a particular favorite. So there's a deck of cards. There's about 70 or 80 cards behind the scenes. It's nice and friendly for making words with 5 E's, 5 T's, 1 Q, 1 Z. And it's a game of skill. So you've got to try to place the letters. Once you place a letter, you can't move it. And you're trying to place letters in such a way that is going to be likely to make words. The more words are better, the longer words are better. 5-letter word is worth 10 points. 2-letter word is only worth 1 point. So if oh, look, that's lucky. It's a random seed I've seen before. So I've already got 22 points and I'm doing extremely well. And so on. Now, within this web-based demo, I can also just get the AI to play. So I haven't got time to play a full game myself. But if we get the AI to play, then it will do this. So every time I click, what's happening is that it's doing Monte Carlo search. It's actually doing information set Monte Carlo search. So it's saying for this A, where shall I place it? And at the moment, only these squares are free. But at the start of the game, we had all 25 squares free. So it's considering all the possible squares. And for each of them, by the way, it doesn't know which letters are coming. It's going to make lots of random rollouts, given possible letters that could be dealt to it. and it will make a decision. It'll place the letter in the position that has the highest average. So that's scored 119. You can play it yourselves on the web after the talk if you're interested. Encourage you to do that. And these are randomized algorithms, so each time, even though the letters get dealt are the same, you'll see it playing in different ways. And 145 is that's a spectacular score. So one thing to notice is that if the simulation model is fast enough, which in this case it is, we can do thousands, perhaps tens of thousands of rollouts per second, then it's making decisions really quickly. So that's an idea of the game. Now I want to go back to the slides, and let's see how LLMs do. So this is pretty interesting. I first started playing with this 2 years ago with ChatGPT at the time. And I'd say, give it the whole thing, prompt it, explain the letters. It's very good at explaining back the rules to me, and so on. And then, interestingly, it talks about having a good strategy, but it can't play the game at all. So, in fact, the letters that got dealt, it just placed them in table order, and then you end up with just a random score at the end. So, a typical random score is about 30 points. Really pretty bad score. So, at the time, it couldn't play it at all. Gemini did something that looked a bit better, but then it started cheating and put an MT in the same grid cell. That's definitely not allowed. Again, it's talking a good game, but it can't actually play it. So what about DeepSeek? Really taught a good game. So this was DeepSeek, I think it's DeepSeek R1. And this was, to be honest, a few months ago, and it might be slightly better now. But it would talk a really interesting sort of strategy. So this thing that it's planning to do here is brilliant. It's saying, for example, vowels in the middle to connect consonants. Let's say I have a row starting with S, then T-A-R-E, that forms stir. This is all exactly how to play the game. It's completely nailed it. Except when it plays, it doesn't play at all. It just works out from the top left. So then a couple of months ago, I tried it with O3 Mini, and this is the first time that any of these chatbots have been better than random. In this case, it scored 54. So nowhere near as good as the Monte Carlo search, but better than the previous ones. And in contrast, when we do the information set Monte Carlo search, the computing time is a few milliseconds per move, whereas using the ChatGPT O4 Mini was taking several seconds per move with really much more computation behind it. So the takeaways from that experiment is that, Brittle's a word game. We might have expected LLMs to be quite good at it, but maybe the spatial nature, the kind of grid arrangement is hard. Somebody suggested to me I should do a 1D version of Griddle and see how good they are at that. I should definitely do that, but I haven't done it yet. Interestingly, they talk a good game, but they cannot translate it into practice. And even the ChatGPT version that you saw being better than random, that's like 10,000 times slower. And so the kind of takeaway from this is that if you've got a simulation model, then definitely use it. So on to another example now. This is the AMAS 2024 Maritime Capture the Flag, organized by the Office of Naval Research. So the control areas of 3 units per team. And this is a capture the flag game. You've got to get to your opponent's flag. So if I'm the red team, I'm going to try and get the blue flag from over here, take it back to my half to score a point. And the blue team are trying to do the opposite thing. The white circles, they're the tagging radius. So if a boat becomes within the tagging radius of an opponent boat, then it'll get sent back to its base to recharge if it's in the opponent half. And if you're in your own half, then you tag the opponent boat. And boats mustn't crash and so on. So the combinatorial action space, we're on at 10 frames a second, and every 10 frames, if you're doing forward plan on this, there are 17 to the power 6 possible actions, considering all your boats and all the 3 opponent boats too. And the planning horizons are long, and the reward landscape is flat or deceptive. So basically, if you try to attack, then you're going to get tagged and sent back, and there are kind of micro points for this. If you crash into one of your own boats, you lose points. So all the kind of things that you're going to do, which might eventually get you points, they risk losing points in the short term. So I wanted to apply SBAI to this, and I had to re-implement the simulator that was provided, which wasn't really fast enough and not really flexible enough for what I needed. And I also did an approximate simulator as well. So I transformed the step-by-step simulator to a discrete event simulation and got a speed up of greater than a factor of 1,000 in doing this. And this makes kind of stupid simplifications that the boats are going to travel in straight lines. And sometimes it's still useful to do that. So what I want to show now is a video showing the AMAS winner against a planning method. So I just want to stop this for a moment to explain what's going to happen. So we're talking about LLMs with SBAI. Now, without a heuristic, we're relying on the true rewards from the environment. And these blue lines are the boats under the multi-unit rolling horizon control. So we're evolving each of these plans, and at the end, you see many of them end in 0. That means having followed this possible plan, I get a score of 0. But most of them end in a large negative score. So minus 2,000, minus 2,000. That means I've hit the boundary or collided with another boat or something. Minus 3,000, even worse. So minus 4,000, yeah. So what we're going to see now, after a while, I'm going to turn on the heuristic, and you'll see the effect of this. The team on the left, this is a team, very, very defensive team that won the 2024 competition. There's been a competition in 2025 as well, and I understand they're planning to run it on real boats, but I haven't had a chance to catch up with what happened with that. So we got this at the moment deliberately slowed down so you can see what's happening. And down the bottom of the screen, please see the scoring conditions. So the captures, the grabs, the tags, the collisions, and so on. And now we've turned on the heuristics, and what you can see now is that there are lots of numbers in between. You know, they're not just kind of whole thousands. And now we're running at full speed. And so what happened then? One of our boats just got tagged and sent back. A couple more got tagged. Now these lines over here, these are the recharge bars, and so our boats now, because these opponents are still recharging, we can just dive in. They've got no tagging radiuses now, and we just keep capturing the flag and scoring lots of points. So now we've scored, the blue team have got 3 captures, 3 grabs, 4 grabs, 4 captures, and so on. So that's the main thing I want to illustrate. Again, this is not just simulation-based AI, this is SBAI with LLMs. That heuristic that you saw, that was written by ChatGPT. So I gave it the key parts of the code, the sort of API for the game, and said, here are the rules, okay, pasted in all the rules, now write me a heuristic to play this. And actually what it came up with didn't work first time, but it was pretty close, and I just made a small adjustment to it. One of the signs was wrong, and we ended up with a reasonably strong player. So that's a nice way that we can use LLMs to generate heuristics, to take in the rules of the game, the aims of the game, and apply it in a more directed way. And after a few efforts with this, it was quite successful. Yeah, and then the next one, we're not going to have time for this. It's just showing the heuristic version beats the plain version. So interestingly, with this competition, there were several RL methods. And like I said, I've not looked at 2025 version, but in 2024, none of them performed well. And since then, there have been some rule changes to the competition. And for the SBAI, we just simply have to update the simulator to reflect that, and there's no retraining required. So another case where the simulation is key to this. I want to go on now to some work that we've been doing using program search for games, using LLMs, and this is going to be some similar things to developing heuristics, but also a bit more general than that. So what we found so far, and there's a paper that's currently under review for IEEE transactions on games, but there's a version already on arXiv, the first version of it. So I would say so far we found that this works quite well for heuristic functions. Many people in many different areas are finding that it's a really good combination of LLMs for generating heuristics, and less well for direct policy generation. But I'd say improving all the time for this too. So here's the overall idea. We've got, for each problem, we have a prompt that we write. We get the LLMs to generate code. Could be a single function, could be a larger piece of code. This gets injected into a safe process. We get executing in the domains, we get the feedback, and this gets iterated many, many times. And that's the idea. Many of you will have seen the work on fund search and Alpha Evolve that's come out of DeepMind. This is similar, applied to the games domain. So interestingly, we've applied this to simple vehicle driving tasks, and the kind of quick version of this is that it's like trying to drive an asteroid-style spaceship to a target, and this is a possible solution that's worked. It's got there and stopped at the target, but it's not done particularly well. So it's overshot and had to come back to it. And these are among the fittest versions that the LLM has found. Because of the low friction and there's no brake, what you have to do is to steer the ship in the direction of it, then turn around and thrust in the opposite direction, and they're not very good at doing that. Quite hard for the LLMs to find a good policy. And interestingly, in the prompt, we recommend using search algorithms because it's much easier if you do that. And the prompt encourages using MCTS. And this is one of the solutions that the LLM came up with. And it said, perform MCTS from the current state. That's a comment that it's put in. So all this code is generated by the LLM. And if you look at this code, if you're at all familiar with MCTS, you realize this is absolutely not MCTS. This is essentially one step look ahead search. So the LLM is, definitely confabulating here and not doing what we asked. Now, for many of these things, if your evaluation framework is strong enough, it's just sort of wasting time when it does this. But it doesn't actually harm you because you're going to pick it up that it's not good at solving the problem. Or it may surprise you, and you may think that you required search for a problem, and actually it finds a very simple heuristic policy that actually works brilliantly. So I think providing the evaluation that you do is strong enough, then it's fairly robust. This is another task, procedural content generation. So the LLMs are tasked with writing a maze generation algorithm. This is a IEEE CIS talk, and part of CIS is evolution computation. So for the EC folks, you'll be pleased to know that the EC algorithm here, this is an evolutionary generated maze where we're trying to place the wall cells to maximize the length of the shortest path between 2 points. So that's a terrible solution. We're just getting there very directly. And that's a better solution found by the LLM. So I say found by the LLM. The LLM's writing an algorithm to generate these. And then this is using evolution directly on the cost function, and that works extremely well. And then some code to play tabletop games. There's a bunch of games, varying complexity. Code Express is reasonably complex. Seven Wonders, very, very complex. And what we're doing here, this is still that program search for games paper. We're evaluating the ability of these to get fed the rules, get fed the API. It's part of our tabletop games framework, fairly complex API. And this is the number of times the iteration of the algorithm has done something useful, produced legal code that has been at all useful. And this BB is better than baseline, beats the baseline, which is one step look ahead, or MCTS. And you can see that some of the times it does. And which model beats the baseline is could be any of them, right? There's no clear winner here. So the moral of the story here is that if you're doing this kind of search for solutions using LLMs, you're best off having a framework where you use lots of LLMs, and each time your evaluation is just going to tell you which one did best. Just a quick mention of some interesting work that's going on. This is LLMs for writing simulation or world models. So World Coder, a model-based LLM agent, and this builds world models by writing code and interacting with the environment. So that it says it all in the title. The last time I looked, I don't think the code was available on GitHub for this. So I've not had to play with it, but I've read the paper, and it's pretty interesting work. So one of the examples is Soccerban, and what they do is run this process in a loop where they're generating state, reward, goals, actions, and training the system to learn a world model. So we're trying to get the LLM to learn a world model that can write an update function. We're given a state, action, and a goal. It will return the new state and the reward. And they're getting some success in doing this. And I find this really fascinating. Now, one of the key things to realize here, though, is that for this example, it's getting trained on a simulator that already knows Soccerman. And so if we're trying to apply this learning to code world models for real world problems that we don't yet have a good simulator for, then we probably need something more than this. But I think it's a really interesting piece of research. So I want to speak a bit more about games competitions. So I think these competitions, they're a really useful way to evaluate the quality of AI agents. And I'm organizing one myself. It's called the Planet Wars competition. And you can see it by the link there or the QR code. So this was a similar game was run as a Google AI challenge, I think back around 2011. And that was really interesting, very, very successful. And it also runs on, I think it's coding game at the moment. But I wanted to do a new version that would be very open-ended, highly configurable, and very easy and automatic to enter. So when I say highly configurable, we can change the rules, the physics, the observability. So for example, here we're playing as a red player, and I can see the planet zone. They're the red ones, the gray ones are neutral, the blue ones are the opponent. But for the neutral and the opponent, I don't know how many ships are on there. I should very quickly explain the rules. So it's what you're trying to do is to take over all the other planets by invading them, basically. And if I send 8 ships to this neutral planet, for example, it looks like where it's headed. If there are fewer than 8 ships on that planet, then I will own it and then start growing new ships there. If there are less than 8, then I'll just subtract 8 from the number there, but it'll still remain neutral. And we're just trying to get as many planets, as many ships as possible. That's basically the game. So it runs at real-time speed. We can change the size, observability, physics, everything about it. We might have a future version in which the planets are moving. For the moment, they're static. So one of the ideas is to use LLMs to solve this. So the LLMs can read the rule. They can read the variations, the parameters for a particular game, and generate on the fly interesting and informed heuristics. So this is just a sample of the game running at the moment. So it runs pretty quickly. The graphics slow it down a lot, so we can run hundreds of games per second. It's very good for training your AI agents. And in this case, the blue is looking quite successful at the moment. One other thing I should mention, the title of the red player is called Greedy Heuristic Agent. This was actually entirely written by ChatGPT, and it's not too bad a player. So I gave it a sample agent, I gave it the API, I gave it the rules of the game, and it provided code that actually wins quite a few games. So it made a really slow start there, and then it attacks really heavily and ends up the clear winner. It's kind of interesting. And with more careful prompting, you could probably do much better than that. So the competition's only just been open for entries, and we're starting to get entries coming in, and hopefully this is going to run and run. So this is running for Gecko 2025 in Malaga, and also IEEE Conference on Games 2025, which also has associated prizes. And Gecko's in July, COG is towards the end of August. So the Rolling Horizon Evolution, this might be the best agent we've got so far. Most of these are in the GitHub repo for you to build on. And there's an interesting submission process as well. So to submit your entry, it's got to be on GitHub, either as a public or private repo. And you just go to the submissions GitHub, open an issue, given the link to the exact commit hash of the agent that you want evaluated. And then we've got a bot that just polls GitHub for new issues on this repo every 10 seconds. And your bot will be evaluated against a set of sample agents. And you get this overall average score. In this case, greedy heuristic agent got an overall score of 70. And then for the finals for each competition, we have a round robin between all the entries. So this is come to the conclusion of my talk. So it's been a bit of a kind of rapid run through various ideas related to this, but you know, it's LLMs are such a fascinating area. That the whole of AI is incredibly fascinating. It's moving at such fast speed. But one thing that I think is definitely true at the moment, and probably forever, is that LLMs themselves are poor at planning. Now, of course, when we talk about AI systems, LLMs more and more just going to be one key component of this. And so how can we make them smarter? Well, I think simulation here is the key. And actually the simulation itself, not just any old simulation, we need a good one with high running speed, the right kind of level of approximation, fast copying ability. We've got to be able to sample over uncertainties, and also have an agent controlled simulation API. So the agent can get the very most out of the simulation in an intelligent way. I think the simulation-based AI is rapidly adaptive, is dynamic, naturally multi-objective. All we need is a preference function to say we prefer this kind of solution to some other one, and the preference function can consider as many aspects of the problem as you like. Now, LLMs can help enormously. They can already generate heuristic functions. They can generate new algorithms. They can perhaps learn to use the simulation in a controlled way. Perhaps even write the simulation. I think it's very early days for that yet. We get some degree of explainability, so explanation through simulation, and yeah, some diagnostics too. So the simulation is causal, so we can use it to reason about the problem domain. There's one more slide that I'm not going to go through, but it'll be in the slide deck. This is just a kind of snapshot of some very interesting research that's going on in related to this. Okay, so I'm going to stop there, and I'd love to take any questions.
Absolutely amazing. Thank you so much. So I have put some notes in the chat. Peter has said it would be great if you can share a PDF of slides or provide a link where people can get them. Is that possible, Simon? Yeah,
Yeah.
Brilliant.
Yeah.
Okay. Anil, I wasn't actually sure what your question was. Why not OpenCC? Does that mean anything to you, Simon? If not, we will ask Anil to come back with a more detailed question.
I think that's to do with the license. Why not an OpenCC license?
Okay.
Yeah.
So while we're waiting for any questions to come in, I definitely have one that I'm really interested in. So looking at agentic AI systems, this is kind of like a pie in the sky, right? Where do you see these fitting in this area of AI simulation in games? Very wide question, I know.
Yeah, sure. So I think this is a core part of agentic AI, but it's a very particular take on it. So what people mean these days by agentic AI, I think are largely LLM-based systems where you're using them as part of your kind of regular workflow to get the sort of jobs that we need to do on a day-to-day basis. And where I see the simulation-based AI coming in for more specialized tasks. So where you need a higher level of intelligence that you can get with general agentic AI. And I'm using agentic AI in the way that it's kind of popularly understood these days, right? Because agentic AI could literally mean any sort of AI agents if we took it really literally. which would certainly include the type of things that I'm talking about with simulation-based AI. Yeah, so I think where it fits, we have more specialist tasks, and this is not sort of any old thing that you could use agentic AI in general for. What we're talking about, imagine you want to solve a particular type of planning task. So for example, we use this for some defense work where you've got military scenarios. You can't just use off the shelf agentic AI for that. You need to develop more detailed simulations of the problems in a more kind of bespoke way, right? And not only that, you need the simulation to be trusted too. So you want something that you can run in a controlled manner. So you might have the AI recommending a course of action to you. And probably you don't want to just accept it. You probably want to test it really thoroughly. And I think this sort of link between the LLMs and the simulation-based AI is just perfect for that.
Just building on that, because no questions have come in just yet. What I was really, really interested with the competition that you were running, and when you said about trusting the solutions that come back and testing them, do you think, given all the caveats of hallucinations, do you think the explanations of the winning solutions or how it's, I mean, we saw from some of your examples there how the LLMs could actually play the game, they understood the game, they said the rules, but they couldn't translate it. Are the
Yeah.
winning games that you're getting in there, can you actually understand them from an explainability side? So the rules that they adapt to
Yeah.
and
Okay. So
generate, I know I'm trying to say it, but yeah.
yeah. So there are two ways to, at least two ways to understand it, right? So in many cases, why we don't care, well, sometimes we don't care about hallucinations. So let's take the case where I'm just using them not to write the simulator, but to use an existing one. Let's take Planet Wars as the example. Then I don't really care how much the LLMs has hallucinated. What I care about is how well it plays the game.
Right.
So that's really the acid test. That's the thing I care most about. But I might also be interested to say, well, okay, it may be top of the league, but actually I can also look through the code it's written as well, and it may be possible to improve on what it's done. So that's the other advantage of having code-based solutions to this. So I'd say, the first approximation is, does it already win? Is it all the most successful bot that we have? If so, fantastic. But we should also probably take time to understand why it's doing what it's doing successfully, and can we even tweak it a bit, and even use human intelligence to try to improve it a bit.
Fantastic. And I won't tell you that absolutely loads of questions have just come in, so I'll try and read them out, okay? I don't know whether you can see the chat, but I'll just for our audience. So, does this notion of having an LLM learn the rules of a game and writing heuristics and models to learn and play the game work for more complex games? The examples were all 2D. Bobby is wondering about 3D worlds like MMOs, RPGs, something closer to real world.
Oh, well, in the paper that I mentioned, the program search for games, some of those games, they're not actually video games, they're tabletop games. But if you ever played Seven Wonders, it's a complex game. So we're already applying this to complex game. Though to be fair, we're not applying it so much to real-time games. I think regarding the 3D games, we should definitely try that. And it depends on having a good enough simulation that's fast enough. In some recent work I did, for example, not actually in the games, this was a defense application. The defense contractors had a very detailed simulation that ran only slightly faster than real time. And the first thing we had to do there was to develop our own simplified simulator that was maybe 1,000, perhaps even 10,000 times faster than the detailed simulator. And then we were able to do effective things with it. So I think, potentially the answer is yes, but there's quite a lot of engineering to do, which I've got to say, well, I find that is very good news as well. So it means that for the moment, as engineers and scientists, we've definitely still got work to do. So if you look at the results of lots of benchmarking papers, including our own, the program search for games, then the LLMs, while they're superhuman in some ways, they're also very limited in other ways. And I think for the moment, there's a lot of scope in trying to make the most of us as humans working with the LLMs to really get things done in the most effective way possible.
Fantastic, thank you. From Anish, what are the key limitations of current RL methods in real-time strategy games like Maritime Capture the Flag?
I think one of the key limitations, and actually, like I said, I really want to see the results of the 2025 competition. But in the 2024 competition, the biggest limitation of the RL methods, I think, was the reward landscape. So where most of the methods failed is that they would run a ton of simulations and never capture the flag. And so the thing about RL is that you need a reward signal to work on. And without the reward signal, you can throw as much computation as you want. But if it's always getting zero or always getting negative reward, it's never going to learn anything. And so that's actually one of the reasons why I find the LLMs such a good mix, because you can feed the rules into the LLM, and that example that I showed, that already generates a decent heuristic. And you saw that before I turned the heuristic on, all the rewards are negative or just zero. And as soon as you have the heuristic, it's saying, well, okay, let's try and do something. So let's reward getting close to the opponent flag. Let's reward other things that might be useful. So there's a bunch of factors there. And all you need often is just enough to kind of nudge the algorithm in the right direction. And then when you do that, the statistics of learning, whether you're doing simulation, search-based AI, or whether you're doing more conventional RL, where you're actually learning long-term policy and value functions, having that reward to latch onto is absolutely crucial.
Fantastic. I'm going to try and fit one more in. There's two left, but one. How does SBAI help in solving the sim to real problem in robot learning?
Yeah, so I think I noticed actually that sim to real is really coming along in robot learning. So where SBAI helps in that, I think it's just maybe the realization that the simulation is key. You typically want to have simulation at multiple different levels. And I think the robot learning folks, they already seem to be, if you see the latest robots that are coming out of, especially coming out of China, they seem to be really getting to grips with this. I think in any particular problem domain, there's a lot of engineering to be done. And the key thing is to have the simulations that are good enough. And for complex domains, you're probably going to need multiple simulations. And the other thing that I've been pushing today is the idea that we need agents that can intelligently use those simulations. So have a range to pick from and use them in the best ways.
Thank you, Simon. I know when we're making the most of your time here, what I've done is I've collected the questions. I know we're not just on the hour, so someone just picked up on that comment and said, can we use SBAI to build the reward model and use the reward model to train the RL agent since it's good for planning?
Well, in a sense, we are doing exactly that, right? So when we do when I talked about those heuristics, I was a little bit vague. So you could have heuristic policies or heuristic value functions. Most of the time today, I've been talking about heuristic value functions. So they are literally a reward model. And so, yes, that's a very effective thing to do.
Hey everybody, I'm really sorry that we did not get round to all your questions, but you'll be able to obtain Simon's slides. I think they'll be posted on IEEE CIS, which is really important. The QR codes there to the competitions are there, the papers, and you name it. And I'm sure you'll all thank me in thanking Simon for giving us this most amazing talk today. I've learned so much, so thank you very much.
Yeah, thanks everyone for attending. Thanks, Keely and Joellen and Noel for organising. And yeah, very much thanks for attending. It's an hour of your valuable time, and I appreciate that.
Thank you, everybody, and hope to see you really soon at the next webinar.
Thanks. Bye now.
Thank you. Bye.